Hello everybody, welcome to Guidancee Education channel. We will see the topic that is discussed in this video. This topic is very important, therefore this video will be a little bit long as I have explained all points in detail. Do not skip the video. We are continuing class 11 chemistry, classification of elements and periodicity of properties. Periodic properties part 6. Under this we will discuss ionization enthalpy. We will answer a few questions. What is ionization enthalpy? How is ionization enthalpy represented? What is the unit of measurement of ionization enthalpy? What is successive ionization enthalpy? What is the trend of successive ionization enthalpy? Explanation and significance of successive ionization enthalpy. If the video is useful, consider subscribing my channel. Press the bell button and all button for notification of more videos like this. Press the like button and also leave your feedbacks as comments in the comment box below. Thank you. We will take up the first question. What is ionization enthalpy? Enthalpy means change in energy. Ionization means converting a neutral atom into an ion. There are two types of ions. The negative ion, which is anion, and the positive ion, which is cation. Ionization enthalpy is the change in energy associated with formation of cation only. For formation of anion, there is a different term. We will see that later on. Cations are formed when electrons are lost. The lost electron gains some energy, so its energy changes. The energy absorbed by the electron which is lost only is considered here. By definition, ionization enthalpy is the minimum amount of energy required to remove the most loosely bound electron from an isolated gaseous atom so as to convert it to a gaseous cation. Energy is needed to convert a substance into gaseous state. That energy is not considered. The most loosely bound electron is found in the valence shell, that is, the outermost shell. The atom should be in the isolated condition. It should not be in the molecular form. It should be an isolated atom. Energy has to be supplied in order to isolate the atom also. That energy also is not considered under ionization enthalpy. So, while determining ionization enthalpy, when energy is applied to the substance, some amount of energy is absorbed to break the intermolecular bond and then the interatomic bonds inside the molecule so that the atoms are isolated. Some amount of energy is also used for conversion of the substance into gaseous state. You know, the energy of particles in the gaseous state is more than that in the liquid or solid state. After formation of the isolated gaseous atom only, the atom absorbs energy to release the electron. This energy alone comes under ionization enthalpy. The cation formed also is in the gaseous state. How is ionization enthalpy represented? Change in energy can be represented as delta H. So, ionization enthalpy is change in energy. It is represented as delta IH. Change in energy associated with ionization. Remember, it is only for formation of cation. It can be represented in the form of an equation. Say, for example, M gaseous plus ionization enthalpy gives M gaseous cation plus electron gaseous. M represents the element. It is not a real symbol. The neutral atom of the element absorbs some energy which is equivalent to its ionization enthalpy and gets converted to the ion of the element and releases one electron. Here we are referring to the first ionization energy. That is energy required for releasing the first loose electron. Different elements will have different values of ionization enthalpy. Ionization enthalpy is also known as ionization potential because a minimum potential difference between the electrodes is needed in the discharge tube for releasing electrons from the isolated gaseous atom. You have already learned the discharge tube experiment. What is the unit of measurement of ionization enthalpy? One unit is electron volt per atom. Electron volt is represented as small letter E, capital letter V, EV. What is 1 electron volt? 1 electron volt is the energy acquired by an electron while moving under a potential difference of 1 volt. You may recall the setup for discharge tube experiment. When a potential difference of 1 volt is set up in the discharge tube, the most loosely bound electron in the outermost shell of one atom acquires some energy so that it can be released. That energy is equal to 1 electron volt. Determining this ionization enthalpy per atom, that is for one atom, will be very tedious. It is easier to measure and express this quantity in kilocalories or kilojoules per mole. First, let us consider kilocalories per mole. We have to convert 1 electron volt into kilocalories per mole. So, first we will convert 1 electron mole into calories per atom. We are considering the energy required for releasing 1 electron per atom. That is the most loosely bound electron from the valence shell, and then find it for calories per mole, and then find kilocalories per mole. 1 electron volt is equal to 3.83 into 10 raised to minus 20 calories per atom. 6.023 into 10 raised to 23 particles make 1 mole. So, 1 electron volt is equal to 3.83 into 10 raised to minus 23 into 6.023 into 10 raised to 23 calories per mole. On simplification, this will be equal to 23.06 into 10 raised to 3 calories per mole. 1000 calories make 1 kilocalorie. So divide this quantity with 10 raised to 3 or multiply it by 10 raised to minus 3. 10 raised to 3 and 10 raised to minus 3 get cancelled. So this becomes equal to 23.06 kilocalorie per mole. Okay. The next unit is kilojoules per mole. We will first convert calories into joules. We get 1 electron volt is equal to 1.602 into 10 raised to minus 19 joules per atom, because 1 calorie is equal to 4.184 joules. This value is per atom. Now let us see it for a mole. Then it is equal to 1.602 into 10 raised to minus 19 into 6.023 into 10 raised to 23 joules per mole. On simplification, this becomes 96.49 into 10 raised to 3 joules per mole. To convert this into kilojoules, divide this by 10 raised to 3. That is, multiply this with 10 raised to minus 3. When 10 raised to 3 and 10 raised to minus 3 get cancelled, and the value becomes 96.49 kilojoules per mole. So you have 3 units mentioned here. Understand this properly. This will come of help while doing problems. Our next topic is successive ionization enthalpy. Successive means something that follows or something which comes after what has already been referred to. Here we have already referred to the ionization enthalpy for the most loosely attached or bound electron. After the release of that electron, other electrons may also be released from the atom in succession, that is one after another. Here also, the subsequent electrons require some energy for them to get released from the attraction of the nucleus. That is, their release also is associated with ionization enthalpy. What will be the ionization enthalpy for the release of successive electrons from the same atom? And how are they represented? We were so far referring to the ionization enthalpy of the release of the first electron. Since successive electrons also can be released from the atom, we need to be very specific while representing the same. Ionization enthalpy for first electron is represented as delta IH1, for the second electron delta IH2, for the third electron delta IH3, and so on. If we are referring to only the ionization enthalpy for the first electron, we are not referring to the successive ionization enthalpy, then we need write only delta IH. We need not specify the number. How do you read this? We read this as first ionization enthalpy, second ionization enthalpy, third ionization enthalpy, etc. Remember, we use the term successive ionization enthalpy for successive electrons in the same atom of one particular element. Now we will see the trend of the successive ionization enthalpy. We will take the example of beryllium. For beryllium, first ionization enthalpy is 899 kilojoules per mole. By absorbing this amount of energy, beryllium loses the most loosely bound electron and gets converted to beryllium positive ion. The atomic number of beryllium is 4. It has 4 protons in its nucleus. The nuclear charge does not change, but among the 4 electrons, it loses 1 electron and acquires a single positive charge. The energy absorbed when the second electron is lost is called the second ionization enthalpy, and it is equal to 1757 kilojoules per mole. It is much more than the first ionization enthalpy. When it loses an additional electron, it gains one more charge and becomes beryllium 2+. Nuclear charge again remains the same, but the number of electrons decrease. The energy absorbed when this beryllium 2+ ion loses one more electron and becomes beryllium 3+ is the third ionization enthalpy. It is equal to 14,850 kilojoules per mole. The ionization enthalpy increases further. So here we see the successive ionization enthalpy goes on increasing. The charge on the ion also goes on increasing because the number of electrons goes on decreasing, keeping the nuclear charge the same. What is the trend of successive ionization enthalpy? First ionization enthalpy less than second ionization enthalpy less than third ionization enthalpy. What is the explanation for this trend? In successive steps, the number of electrons goes on decreasing by 1 and the nuclear charge remains the same. So, the nuclear attraction on the electrons become more in each step. Therefore, more energy has to be absorbed by the electron in order to release itself or to break itself from the nuclear effect. What is the significance of successive ionization enthalpy? The relative stability of various oxidation states can be easily predicted on the basis of successive ionization enthalpies. You know what is oxidation state? The oxidation state of beryllium plus is +1 and that of beryllium 2+ is +2 and that of beryllium 3+ is +3. Corresponding ionization enthalpies help to predict which one of these is more stable. Let us see the criteria which decides this. If the difference in the two successive ionization enthalpies is approximately equal to 10 to 15 electron volts per atom, that is 965 to 1450 kilojoules per mole or less, the lower oxidation state is not stable. That is, for lower oxidation state to be stable, the value of the difference between the two successive ionization enthalpies should be above this value. That is, higher than this value. We already have the three successive ionization enthalpy for beryllium. Let us see which one of the ion will be more stable. The difference between the second ionization enthalpy and first ionization enthalpy is 858 kilojoules, which is less than the limit that is shown above. So, +1 oxidation state is not stable for beryllium. The difference between the third ionization enthalpy and second ionization enthalpy is equal to 13,093 kilojoules, which is much higher than the upper limit that is shown above. The lower oxidation state in this pair is +2 oxidation state. If the difference in the ionization enthalpy is more than the higher limit, that is 15 electron volts, then the lower oxidation state, namely +2 oxidation state, is more stable. We will note down that point. If the difference in the two successive ionization enthalpy is more than 15 electron volt per atom or 1450 kilojoules per mole, the lower oxidation state is stable. We will do one more example. Aluminium, atomic number 13. First four successive ionization enthalpies for aluminium are given here. The values are in kilojoules per mole. The oxidation state of aluminium plus is +1. For aluminium 2 plus it is +2. For aluminium 3 plus it is +3. And aluminium 4 plus it is +4. Which one will be more stable? We will find the difference between successive ionization enthalpies. You can notice here that the difference between second ionization enthalpy and first ionization enthalpy is 1218 kilojoules. It is less than the upper limit, that is 1450 kilojoules. So, +1 oxidation state is not stable. The difference between third ionization enthalpy and second ionization enthalpy is only 963 kilojoules per mole. This is less than the lower limit, that is 965 kilojoules per mole. So the lower oxidation state, namely +2, is not stable. The difference between fourth ionization enthalpy and third ionization enthalpy is 8822 kilojoules, which is greater than the upper limit, that is 1450 kilojoules per mole. So, +3 oxidation state is more stable than the rest. So, successive ionization enthalpy has great significance. If you think the video was useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you're watching without subscribing my channel, do subscribe it now. Subscriptions are totally free as usual. And also press the bell button and all button for notification of more videos like this. Thank you very much. Bye for the present. Take care.